You know how sometimes you look up at the night sky and it just hits you? How unbelievably huge everything is.
Oh, absolutely. It's humbling, isn't it?
Totally. And then there's that little pang of disappointment, knowing that even if we find amazing planets, they're just so far away.
Light years away, yeah. It feels like this insurmountable barrier sometimes. You learn all this incredible stuff, but the idea of actually going there...
Forget about it, right? It seems impossible. But what if there was a way? Like a shortcut.
Ah, the big what if.
Yeah. What if you could just, I don't know, hop across millions of light years, maybe cover that distance in just, say, months?
That's the dream, isn't it? That's the kind of question that fuels so much science fiction, but also, surprisingly, some real scientific thought. It tapped into that deep human desire to explore, to find those aha moments.
Exactly. And that brings us perfectly to today's deep dive. Based on some of the material we've both looked at, we're talking about wormholes.
The cosmic shortcuts.
Right. And when you say wormholes, I bet a lot of people immediately think of Interstellar, that scene near Saturn.
The swirling tunnel, yeah. Very digitally striking.
Totally. Cooper and the crew just zip through to another galaxy. It feels like pure movie magic.
It does, but what's fascinating and something highlighted in the research is that the core idea, this concept of a shortcut through space-time, it actually has roots in serious physics.
Seriously. So it's not just science fiction.
Not entirely, no. I mean, Interstellar definitely took liberties, but the fundamental concept, that comes from real theoretical work. So our mission today really is to dig into the science behind wormholes, drawing on some of those foundational physics ideas.
Okay, let's do it. So if we're talking about bending space to make a shortcut, I mean, where do you even start with something as wild as a wormhole?
Well, the logical place, the bedrock, really is Einstein's theory of relativity, his general theory specifically.
Right, Einstein. Gravity, space-time.
Exactly. His work, formulated in these incredibly dense equations, just completely revolutionized how we understand gravity and the universe's structure. He first presented them back on November 25th, 1915.
1915, wow.
Yeah, at the Prussian Academy of Sciences in Berlin. A huge moment.
And those equations, I've seen the short version written down, Gim plus something equals something else. It looks pretty intimidating.
Oh, it is. Gim plus A to G tin. It's definitely not simple math. But the core idea, the takeaway, is what it describes.
Which is?
It describes how matter and energy actually warp or curve the fabric of space-time. Remember Einstein's analogy?
The sort of rubber sheet or mesh.
Exactly. Put a heavy ball on it and it dips, it curves.
Yeah.
Massive things, planets and stars do that to space-time. More mass, more curve. And it's not just space, it's space and time woven together, this flexible fabric.
Okay, I can picture that. So the universe isn't just empty space, it's more like this dynamic stage that gets shaped by everything in it.
You got it. And here's where it gets really interesting. Even Einstein couldn't immediately find a complete solution to his own equations.
Really? Even him?
Yep. The first person to find an exact solution was Carl Schwarzschild, just a year later, 1916.
Schwarzschild, okay.
And his solution was monumental. It helped us grasp the concept of a singularity, what happens when matter gets infinitely dense. His math basically predicted black holes.
Way back then, before we ever saw one.
Decades before. We only got that first direct image in 2019, right? But Schwarzschild's math said they should exist way back in 1916. It really shows how powerful theoretical physics can be, predicting these mind-bending things.
That's incredible. So the same rules that describe how planets orbit also predicted black holes. That definitely adds weight to, well, other possibilities those equations might hold.
Precisely. And that's the crucial link for us today. Wormholes are another possible, valid solution to the very same Einstein field equations.
Another solution. How does that work?
Well, think back to maybe high school math. A simple quadratic equation can have two correct answers, right?
Yeah, okay.
Einstein's equations are vastly more complex, so they can have multiple different solutions, each describing a potential physical reality allowed by those fundamental laws. Black holes are one solution. Wormholes are another.
Okay, that makes sense. One rule book, different possible outcomes in the universe. So this wormhole solution, does it have a fancy scientific name?
It does. It's called the Einstein-Rosen bridge.
Einstein-Rosen, after Albert Einstein and
Ethan Rosen, yeah, his colleague. They worked it out together and published it in 1935.
The Einstein-Rosen bridge sounds pretty epic. So what is it, in simple terms?
Basically, it's a theoretical tunnel or bridge connecting two different points in space-time, a shortcut.
Like folding a piece of paper.
Exactly like that. That's the classic 2D analogy. You have point A and point B far apart on the flat paper. Draw a line, that's a long way, but fold the paper.
Fold it. So A and B are right next to each other in 3D space.
Right. Then you could, theoretically, poke a hole straight through, connecting A and B directly. A much shorter path.
So the wormhole is that hole through the folded space.
Pretty much. Now, scale that up. Our universe is 3D space, right? A wormhole would theoretically bend our 3D space through a hypothetical fourth spatial dimension.
Whoa. Okay, fourth dimension.
Yeah, not time, but another spatial dimension, just for the geometry to work. It allows space-time to curve back on itself, connecting two very distant points directly. Think about a world map.
Okay.
Flying from, say, Delhi to New York looked like a long curve on a flat map. But on the actual 3D globe, the shortest path is different, right? It goes over the pole.
Right, a great circle route.
Kind of like that. The wormhole uses a higher dimension to create a geometrically shorter path through space-time.
That really changes how you think about cosmic distances, makes them feel maybe not so final. I remember reading about John Wheeler's analogy, too.
The worm in the apple.
Yeah, that one stuck with me.
It's a great one. The worm doesn't have to crawl all the way around the outside of the apple skin, right?
It just burrows straight through the middle, takes a shortcut.
That's the essence of a wormhole. Wheeler actually coined the term wormhole because of that analogy.
So if we could see one, what would it look like? Not the 2D paper thing, but like, really?
Well, those 2D diagrams are useful conceptually, the tunnel connecting two mounds on a curved sheet. But in our 3D space, bending through a fourth dimension, it probably wouldn't look like a tunnel entrance.
No, what then?
More likely, it might appear as a sphere, like a spherical portal or window.
It's a sphere, huh?
Yeah, imagine looking at it. You'd see the sphere maybe shimmering or distorting the space around it. As you got closer, the view through the sphere would show you the distant location at the other end. And looking back...
The place you came from would shrink away super fast, like an interstellar.
Exactly like that visual. Yeah, some visualizations online try to capture it. Space would look incredibly warped around the edges of this sphere.
That's a wild image. But we have to keep reminding ourselves, this is all theoretical, right? We haven't actually found one.
Absolutely crucial point.
Yes.
Wormholes remain purely theoretical. They fit the math, they're a valid solution to Einstein's equations, scientists have explored their properties, but zero observational evidence. We haven't seen anything that looks or acts like a wormhole mouth.
Which, of course, leads to even more speculation. Like, if they did exist, could they be used for time travel?
That's a big one. It sort of naturally falls out of the physics.
Yeah.
If you can traverse a huge distance almost instantaneously through a wormhole.
You'd be effectively going faster than light compared to someone taking the long way around.
Exactly. And according to relativity, faster than light travel, or paths like these through space-time, could potentially lead to time travel scenarios, going back in time or forward.
Which opens up a whole can of paradoxes, I bet.
Oh, a massive can of worms, you might say. Grandfather paradox, all that stuff. It's a huge theoretical tangle that comes along with traversable wormholes.
Okay, so let's just hypothetically assume they're real.
Yeah.
And stable somehow. What are the hurdles for a person, like, actually using one?
Well, the first giant hurdle is making one, or finding one and keeping it open.
Keeping it open.
Yeah, the theory suggests that to create such an extreme warp in space-time, you'd need immense gravitational forces. Or, possibly, something exotic.
Like what?
Well, one idea, going back to Einstein and Rosen, was a connection to black holes.
Right, because black holes have that insane gravity. So maybe one end of a wormhole is a black hole?
That was their initial thought, but there's a problem. If you fall into a black hole,
You're not coming out. Spaghettification and singularity, game over.
pretty much. So if one end is a black hole, it's a one-way trip to oblivion, not a traversable shortcut. For a wormhole, you could actually go through and come out the other side. You'd need, well, something else, something to counteract the collapse.
Something else? Like what?
This is where another highly theoretical concept enters the picture. White holes.
White holes. Okay, I've heard the term. They're supposed to be the opposite of black holes.
Exactly. Anti-black holes, in a way. Also a valid, though much more speculative, solution to Einstein's equations.
So instead of sucking everything in,
They violently expel matter and energy. A black hole has an event horizon, a point of no return. Nothing escapes.
Yeah.
A white hole would theoretically have an event horizon of no admission.
nothing can get in.
Correct. But stuff can come out,
Yeah.
which would make them appear incredibly bright, luminous objects. The term white hole was coined by Russian physicist Igor Novikov in 1964. People sometimes describe them as time-reversed black holes.
Time reverse? What? Okay, but wait. We know how black holes form, right? Giant stars collapse.
Yes, we have a pretty solid understanding of stellar collapse leading to black holes.
Yes. Where would white holes come from? Do stars uncollapse?
Good question. And that's the big mystery. We don't really have a known physical mechanism for forming white holes in the current universe. Their existence is way more speculative than black holes.
So just pure theory then?
Mostly. There's some fringe ideas. One is that maybe the Big Bang itself was a kind of primordial white hole event, the origin point from which everything expanded.
The whole universe starting from a white hole.
It's an idea some have explored. Another, even more speculative thought came from Stephen Hawking. He wondered if black holes, as they evaporate over eons through Hawking radiation,
They shrink, right?
they shrink, lose mass, and maybe, just maybe, at the very end of their life, they could transition, perhaps briefly, into a white hole before disappearing completely. A final burst.
So maybe black holes and white holes are two sides of the same coin, somehow connected.
Potentially. It connects back to the Einstein-Rosen bridge idea, too. Maybe a wormhole connects a black hole entrance to a white hole exit somewhere else, or sometime else entirely. But again, very deep into theoretical territory here.
Okay, wow. So we started with wanting a shortcut across space. And we've ended up with Einstein's mind-bending equations, predictions of black holes that turned out to be real, and then these other solutions, wormholes, potentially linked to hypothetical white holes born from maybe the Big Bang or dying black holes. It's
a lot. It absolutely is. It shows how complex and interconnected these ideas are in theoretical physics. So to kind of wrap up the main points, wormholes are this fascinating mathematically possible consequence of relativity. They offer this tantalizing glimpse of a solution to cosmic distances. But their actual existence, let alone whether you could actually travel through one, is totally unproven. It's still firmly science fiction for now, and it raises all these other deep questions about things like white holes, time travel, paradoxes.
It really brings us back to that feeling at the start, looking at the night sky, that vastness. But instead of just feeling like a dead end, it feels more, I don't know, like a canvas for these incredibly strange and wonderful possibilities that scientists are still trying to figure out.
That's a great way to put it. It's not a barrier necessarily, but an invitation to keep pushing the boundaries of what we think is possible, using the tools of mathematics and theoretical physics.
So, a final thought to leave people chewing on. If wormholes could connect different points in space-time, could they connect more, like maybe different universes, or bridge vast gaps in time?
That's the ultimate extension, isn't it? If you can tunnel through space-time, where else could those tunnels lead? Parallel universes, the distant past or future. The implications for our understanding of reality itself would be, well, profound. Doesn't even begin to cover it.
Definitely something to ponder. Maybe revisit some of those wilder ideas and the sources we looked at. A lot to think about.